Welcome to class. In this video, we would begin our discussion into the Cauchy's theorem, particularly the first integral theorem and the second integral theorem. So for this series, we are starting off with the Cauchy's first integral theorem. The theorem itself states, let f of z be a single-valued and analytic function throughout a simply connected region R. Then, the line integral of f of z around any closed path C which lies entirely inside R is 0. What this means is, if I integrate f of z dz over that closed path C, the result I'm going to get is always going to be 0. So this exactly is the Cauchy's first integral theorem. Now in this video, we would be proving this Cauchy's theorem to see exactly how it can be proved. As always, make sure to like, share, and subscribe, and turn on your notifications so you do not miss any of our videos. Now, of course, the very first thing we want to do is have a good understanding of how this function can be defined. Remember that we have been told that f of z is single valued and analytic. So let us first and foremost start with the single value, the variable z itself. Of course, in its algebraic form, we can define z as x plus iy, which would mean that if we differentiate all sides, we can have the z to be equal to dx plus I dy. So this way, we already have our first differential. Now, the next thing is for us to think about our function. In this case, right, we can define the function as the standard complex function, which of course we know as u xy plus I v xy, right, where u is the real part of the function and then v is indeed the imaginary part of the function. So it means in detail that we can define the entirety of this integral, the left-hand side of this integral, by this function and this differential. And this is very, very important. So now let us see how exactly this would factor out into. Now, if we consider the left-hand side, we would have that the integral over c of f of z dz can be written as the integral over c f of z replaced by this. So we have u of x y plus I v of x y, then dz replaced by dx plus I y. Now, if we have this, of course, we can do a preliminary expansion and have this written as, we can write this in short form u and v, so we don't waste so much writing space. We can have this as u plus iv vx plus, of course, u plus iv I dy, right? And of course, we can go further to expand. This in turn gives us integral over c u dx plus iv dx plus iu dy. Then I times I gives us I squared, which of course is minus 1. That will be minus v dy. So if we collect the real parts together, which means the part without the I values, we would have this integral reduced to integral over c u dx minus v dy, then plus I on this side v dx plus u dy. Now, this is plenty as far as this is concerned. Now, by property of integrals, we can split this integral into two, such that we will now have that the integral f of z dz can be written as the integral over c of u dx minus v dy plus I integral over c of v dx plus u dy. So we have this as the first part of our integral. We have this as the second part of our integral. This can be deduced to be the real part of our integral, and this can be deduced to be the imaginary part of our integral, P and Q. Now, listing it as P and Q makes it easier for us to solve when it comes to finding the values of this integral. As always, we will consider P separately, and then we would also consider Q separately, so we have an idea of what this means. Now, remember, there is a lot of premise that has been made here. The conclusion is that the line integral has to be 0. However, the premise is that f of z is single valued and analytic, right, throughout the simply connected region. Now, knowing this as the premise is very, very important. Remember, the premise of a statement gives you the tools you need in order to be able to solve your conclusion. So for this premise now, we have the fact that it's single valued and analytic, which means that we can use the conditions of being analytic, which is the fact that if it's analytic, it means the first 4 partial derivatives are continuous. It also means it satisfies the Cauchy-Riemann equation, right? We also have the fact that since it is single valued and analytic, it means for a fact that it will definitely satisfy the Green's theorem. So if it satisfies the Green's theorem, which of course also works under the condition of analyticity, because the Green's theorem needs the first partial derivatives to also be continuous, then it means that I have most of the tools in order to break this down. Now, you might wonder, why exactly is Green's theorem important? The reason why Green's theorem is very, very important for us is because we remember we have already written this in terms of dx and dy. If you remember our definition of Green's theorem or the statement of the Green's theorem, we realize that we always have an integral that contains the dx and dy representation. If you have forgotten a bit about this, make sure to take a pause and watch our video on the Green's theorem so that you can understand this extensively. Now, we would apply these conditions and also prove to see exactly what we have. Now, we'll take the first part. For P, right, we know that since f of z is indeed single valued and also indeed analytic, then of course u and v, right, and the first partial derivatives with respect to x and y are continuous. And that's not all, right? By the Green's theorem, because we now have all the premises needed for the Green's theorem, it means that we could rewrite u and v in terms of the Green's theorem and would have the integral over c of u dx plus v dy can be written as the double integral over the region R of, in this case, del x v minus del y u dx dy. This is just the statement as verifiable by or via the Green's theorem, right? Now, this is very, very interesting. Also, you would realize that in this case, if you have this notation, it is also important to note that remember that P is u dx minus v dy. Now, this won't affect much. Why won't it affect much? Because it just means that we are going to just be making substitutions based off the Green's theorem. So how exactly is that substitution going to look like? Of course, we can first and foremost rewrite it, and we'll see that the integral over c of u dx minus v dy in this case, right? So in essence, right, in essence, it just means that your function of v has been replaced by minus v, and that would affect on the right hand side. So in this case, minus v dy will just simply give us integral over r of del x of minus v minus del y of u dx dy. Now we can decide to write this in a much more shorthand form as integral over r minus v subscript x minus u subscript y. This is an alternative notation of writing the partial derivative, which is standard in literature. Now, remember, the first partial derivatives with respect to x and y are continuous, hence the reason why we can apply the Green's theorem. Also, do not forget that it is analytic. F of z is analytic, which means that it satisfies the Cauchy-Riemann equation. So I can say that since f of z satisfies the Cauchy-Riemann equations, which is CRE for short, and if you're wondering what the Cauchy-Riemann equations are, we also have a video in our playlist detailing what the Cauchy-Riemann equations are, so you can also give it a watch for understanding. Now, of course, the Cauchy-Riemann equation is telling you that ux, which is the partial derivative of u with respect to x, must be equal to the partial derivative of v with respect to y, and the partial derivative of v with respect to x must be equal to the negative of the partial derivative of u with respect to y. So if this is the case, it means if you look at this function, since we already know that the integral over c, which of course we can just rewrite as p, which we'll do shortly, of v dy is equal to the integral over r of minus vx minus uy dx dy, it means immediately that we can replace this via Cauchy-Riemann equation. So this would imply immediately that p, which of course is this left-hand side, is equal to the integral over r. If we decide to replace vx by minus uy, minus times minus would give you a positive ui, so you'd have that ui minus ui dx dy. This essentially gives you 0, so this tells you that p is equal to 0. This is the first part of our proof. So we have shown that the real part of the integral is 0, which is p. The next thing is for us to go through the same process for q and see if, in the case of q, the same conditions hold and q is also equal to 0. So let's see. For q, and to bring it back to our notice, what q is, remember, q equals the integral over c v dx plus u dy. This is what we know as q. Now, remember that if we apply the Green's theorem yet again, based off q, we would have that by the Green's theorem, since we are still in f of z, so all conditions to satisfy, by the Green's theorem would have that the integral over c of v dx plus u dy, no need to worry about signs here, will be equal to the double integral over r of del x of u, right, because there's obviously an alternation here, minus del y of v dx dy. And if you write this in shorthand, as always, would have this to be integral over r of ux minus vy dx dy. Of course, this is q. Do not forget that it also satisfies the Cauchy-Riemann equations, and by the Cauchy-Riemann equations, we see that what is important here is the fact that ux equals vy. So it means immediately that q will be equal to the double integral over r of ux can be replaced by vy. Hence, we see that this will cancel out. Thus, we would have immediately that q equals 0. And there we go. So now, let's bring our integral back. Do not forget that the integral over c of f of z dz equals P plus IQ, right? And P is 0, Q is 0. Therefore, it means that the integral over C of f of z, the z is indeed equal to 0. And there we go. So we see immediately that the Cauchy-Riemann equation and the Green's theorem are essential tools when it comes to proving the Cauchy's theorem, right? The Cauchy's first integral theorem, which is usually just referred to as the Cauchy's theorem. Without the premise of analyticity, we would have had an issue in applying the Green's theorem and the CRE, because without it being an analytic function, you won't know if it satisfies the Cauchy-Riemann equation or not. But by the fact that it's an analytic function, we know first and foremost that its first partial derivatives are continuous. We know that it satisfies the Cauchy-Riemann equation. And in fact, being the fact that the first partial derivatives are continuous, and of course u and v are also continuous, that already gives us all the necessary premises we need for the Green's theorem as well. So putting that all together now makes it very, very straightforward in solving or improving the Cauchy's theorem. I hope this was quite easily done for you. Of course, if you have any questions, do not hesitate to let me know in the comments. As always, make sure to like, share, and subscribe, and turn on your notifications so that you do not miss any of our videos.